Remember that we have a certain setting where we're looking at some probability space with a sigma, or at least some measurable space, right? With a cylinder sigma algebra. So the F is the cylinder sigma algebra. That we define this. And the important thing is that then we take some process, right? So usually you know that it's by xt of such an omega. This was just omega t, right? So we have the canonical process in this space, and then we have the canonical filtration, which was just to take the sigma algebra generated by the first t+1 elements in the sequence. And this, I will now start using ft to denote this. Whenever I write ft, it's the filtration that goes with the process that we're talking about. Okay, I mean, sometimes on the board, I don't specify exactly what we're doing, but this is the setting that we're going to do for basically the whole course. Usually this will be a random walk. And we also defined the stopping time. Remember, we defined what a stopping time is. It's a function from G to time can be infinite, okay? And this function is measurable. So this is a stopping time whenever this event is measurable with respect to the canonical filtration. So if you have a filtration, you can talk about what a stopping
the end. T.
Yeah.
Omega. Is our omega?
What?
This is our omega.
This is our omega. Yes. This is our omega. Base of sequences. Okay, so it looks at a sequence, an infinite sequence. It gives a number. This number is it wants to tell you some time. So it could also be infinite. And we said it's called stopping time if you can decide whether the time happened or not by time t, by time little t. You can decide that by only observing things that come from the information of the first t steps of your process. You don't need the future in order to determine your time, okay? Typically, what you should be thinking of is the hitting time of a set, the first time you enter a set, something like that. So, and today I want to do the strong Markov property. Okay, so we have the Markov chain. Let's go back. Markov chains. Remember what a Markov chain, the initial data was some probability measure on G, right? And on a set. So G is now just a set. We're not using anything about the groups or anything. And we also had P, which is a G by G matrix. I'm going to write matrix, but of course it's infinite, so it's an operator. But right, we discussed this, and it's a stochastic matrix. So I think sum to 1. I mean, and okay, so these are always probability measures. I can also write it like this. With a T x dot. What is that? That is a vector, right? G indexed vector. So I can say that this is a probability measure for every x. And that's the same thing as saying stochastic row sum up to 1. And this tells you if you're at x, what's how to jump to a new state y. And so this is the data you need in order to determine what a Markov chain does, right? We saw, and then the Markov property is the following property, right? If we have anything inside, yeah. So let me write it in 2 different ways. Okay. So one way is I can look at the probability. Okay. And this can be any probability. So, okay, put some new here, it doesn't matter. Starting distribution. Okay, any probability. Conditional probability. So I take under this space the conditional probability that x t plus n, okay, or let's do n plus t is equal to something. Some little x. Okay, so I'm looking at the conditional probability, conditional what? Conditional on everything that happened up to time t. Conditional on anything that happened up to time t. Now, we phrased it last time, we phrased it slightly different. I said for any event inside ft, blah, 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 but it really boils down to this statement. This is a random variable, right? This is a random variable. Okay? This is a random variable. And so if you know everything that happened up to time t, then the probability that at time, sorry, not time t, time n, doesn't matter, but so if you know everything that happened at time n, then what is the probability that at time n plus t you're at x? Well, what that probability is just t steps of a Markov chain with starting distribution, the distribution you get for xn from this conditional. Okay? So this is equal to almost surely, like surely, but anyway, because it's equality between random variables, this is equal to the probability. Now, what am I going to start from? I'm going to put a weird thing here. I'm going to say delta xn. Delta xn. What is delta xn? This is a random object, but it's measurable with respect to this. I can take delta measure with respect to that object. So you start at xn. If you know where xn is, this gives you a deterministic thing here, but this is random. Okay, so in terms, that's the randomness here. This is a random variable, right? Measurable with respect to this. This is a random variable with respect to this. That's all the randomness there is in here. And then inside this probability, we have this is just a probability that a Markov chain of t steps reaches x. So I can write this xt is equal to x.
But this is like a different xt, right?
Well, what I wrote here, this is xn, this goes with this, right? And the probability, this is an event. Just measuring this event. This is not not random, like the probability, okay. You have to understand that these are, yeah.
I probably making.
Formally, this is the same thing, okay? What this says is you sum over all possibilities for xn. Okay, let me make this much clearer. I can sum over all the possibilities for xn, right? I can look at the
probability
indicator. No, it's random.
Oh.
Indicator that xn is equal to y. Okay, then I start from y. Now I'm going to write something else instead of. So I start from y. Ask what is the probability. So this is just a number. This is just a number. I don't care about this number. Right? So this xt can't be this xn because here it's random. This is function of omega. This is just a number. Okay. So, but I can write it if it confuses you, I can write it this way.
No, okay.
Ptyx, and this sum as a random variable, as a function of omega. Where's omega? Omega gets stuck in here. As a function of omega, this looks like this. Tth power of the matrix at the point xn x. All of these things say the same thing. They're all random, they're all functions of omega. Here you plug in the omega 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 into the conditional expectation. All of them are functions of omega. They say the same thing. This is the Markov property. The Markov property says, if you know what happened up to time n, what the rest of the chain looks like is, well, first of all, you have to understand how you start, okay? How the distribution starts. Then the rest is okay.
How it starts, this goes into the indicator of x and equals y. Then the nu, like we lost the nu, but it goes into the dxn, delta xn.
Yeah, the delta xn,
Yeah.
right? For every omega, you get a different xn. So you get a different starting measure. What you think about is that suppose you condition the time n, and you have an idea of how xn is distributed at time n. So with some probability it's here, some probability it's here, right? And you have to, first you press the button, which samples your xn. Then once you know your xn, you know that it continues like a Markov chain, deterministically started at that xn. And that's what this is. Okay, so they all say the same thing. Now what I'm going to do is I'm going to make this, I want to make this guy Today, what we're going to do is we're going to do a strong Markov property. I'm going to strengthen this problem. This is actually very easy. We just sum things, check every event inside Fn or something like that, right? So the proof of this was very easy, just a basic conditional expectation argument that everything is countable, so it's very easy to do this. But I want to put a big T instead of the N here. I want to put a big T here. Okay, I want to put a stopping time there. Well, maybe any random time, but it turns out what you need is stopping times, right? So, but then what does that mean? I mean, I have to put this. What is ft? What is f of a random time? It's not defined. You don't have any definition for that. And and if you want to do this, then also you have to do well, okay. Here you can understand, but you see that if I want to put an xt here, I have to make sure that t is finite, almost surely. Okay? We have to be very careful. And this is going to be the content of the strong Markov problem. So now we're going to do the strong Markov property. Okay, let me put this on the board, maybe. I hope I'm on my own. Just write the regular Markov property. I'm going to write it here. It's just this. Okay, so all it tells you, if you know what happened time n, you continue like a Markov chain. By the way, independent of what happened up to time n, right? All you need to know, the only thing you need to know is where you were at time n, and that's it. Okay. First, I have to tell you what is f sub big T for a stopping time t, right? I have to define what that means. Okay. So, exercise. Let t be a stopping time. We defined what that means, right? We have some process, we have some filtration. Okay. Fine. Show that what you need to show is that the following collection, you take all the events A inside your space, such that, well, if you take all the events, I get the full sigma algebra, right? Or the whole cylinder. All cylinder events, such that for every T, if I take A and I intersect A with the event T less than or equal to T, so where does this guy live? This guy I know lives in FT. This guy is general. What I'm requiring is that no matter which T you take, when you do this intersection, which gives you a priori a general event, it has to be special in the sense that this should belong to FT. You see, I don't take every single cylinder event, I just take some cylinder events. And this is just a collection of events. It's a set of sets, a set of subsets. And you need to show that this forms a sigma algebra. Okay? So this is a sigma algebra. It's all the events such that if I add the information that T already happened, then you can also determine that the event happened or not. Okay? Okay? So this is the exercise. Show this. I mean, it's very easy to show this in algebra. There are 3 things you need to show, and they're very easy. Okay, this is sigma algebra, and then we have, once we have this exercise definition, if we want to write ft for stopping time, okay, ft for stopping time, which is the same as sigma of x0 up to xt. This is not necessarily defined. This is only a symbol, what I'm writing here. This is only a symbol, right? This xt does not have to be defined. They don't know what x infinity is. Okay? And this is just a symbol, a way of writing it, because I don't always have the f's. Right? See this symbol, this is what it means. This is, we define this to be the set of all this set. Okay? Let's call that f sub big T or sigma of x0 up to xt.
So f of big T is always defined.
Yes, so f of big T, sigma of x0 up to xt, this is just a fancy way of writing this set. Right? There's nothing random here. It's deterministic sigma algebra. It's sigma algebra. It doesn't live in a space where you have a probability measure. Okay, so important to okay.
Is there a thing, a random sigma algebra?
What?
Is there a thing, a random sigma algebra?
Well, you could put a probability measure on sigma algebras or something like that. You could, but I'm just saying there's no. This is not like a
Yeah.
Your random stopping time. You evaluate it, then you look at the sigma algebra at that time. That's not what this means. This is just some sigma algebra in my space, which is different from the others, kind of some weird combination. It is all the information you can get from looking at your process up to the stopping time. That's what it is. It's all the information I can get from my process, my infinite process, where I only am allowed to look at it up to the stopping time. So if the stopping time is the first hitting time of a set, right? I get many sequences, many possible things. They don't have to necessarily stop at a fixed time. Maybe that set, maybe the stopping time is unbounded, but maybe it's even could be infinite. But what is the information I can get from only observing the Markov chain and not looking at it? Once it hits the set, I don't look at it. What can I ask about that? So if you think about it that way, I mean, that's just one example, but if you think about it that way, then you'll see immediately that the examples that I'm going to write down are immediate. But of course, this is true for general stopping time. So I'm going to write down some examples.
Can I ask you a question?
Yes.
I'm not sure I fully understand the idea of stopping time. Like, the idea is not that you want to go by like the integers time 2, you want to go by random times.
So it's a random time. It looks at a sequence and outputs a number. So it's a random time, right? For every sequence, it gives you a number, maybe infinite, not a number, but a time, which means also could be infinity. And but you can determine it by only observing the past. So the definition that was written is that if you want to determine, I want to ask for any t, I want to ask whether my stopping time happened or not. Okay, did it already occur?
For a fixed omega.
No, this is an event.
Oh, okay.
Okay, all the omegas such that they happened, the random time happens before time 1000. That's measurable with respect to the 1000th filtration or the first 1001 steps of this. Okay. That's what defines the stopping time. You can determine it by only observing. You look, and at every point you can decide, did it happen or did it not, without knowing what's going to happen. For example, first time of hitting a set, that's a stopping. Okay, but the last time of being in a set is not a stopping. Because by looking
You don't know that it was the last time.
Yeah, you don't know
the best.
from looking up to time little t, you can't decide if it happened or not because maybe you'll be in the set again. Maybe not. You don't know. Okay. Okay. So let's do some examples. First of all, we would like that the stopping time itself is measurable with respect to this sigma algebra. So t, let's write it this way, t less than or equal to t, this event is always inside ft. Proof, you intersect it with its, right? Well, you have to be careful. I mean, that's a fixed t, and then you have to intersect it with all other n's, say, right? When you intersect it with n, remember, filtrations are increasing, so you always get the smaller one, right? Okay, so that's one thing. And this is the same thing as saying, I mean, since this holds for every t, this is the same thing as saying that t is measurable with respect to ft, right? If you pull back any singleton in this case, because it's just discrete, then you get an event.
It's not the sigma algebra generated by T or
No, it's not the sigma algebra generated by T. You see more things. You also see what the process does, not just what the time.
okay.
Okay, for example, here's something. If T, so this is one example, and here's another example. If T is finite almost surely, then I can define what xt is, right? And I can define what xt to measure zero, so it's well defined. And then
all defined.
then xt is measurable. Let me just write belongs to ft. I mean, when I write a random variable belongs to a sigma algebra, what I mean is it's measurable with access. Okay? So you also know where it is, not just the time. You also know where it is at that time. Okay? In fact, the whole sequence, x0 up to x big T, would be just the whole sequence would be measurable with respect to that.
Why did we need it to be?
Because I can't write this. If I don't know the T is finite, there's no way of writing this. But okay, let me take care of that technical problem. So we can do this. We can define. What do I want? Yeah. So we can define a random variable y. So let z be any say g valued random variable. So this just means it's a function from measurable function with respect to the cylinders from g to the n to g, right? And like our process, like our xt's, okay? And then we can define y to be the following. We can define y to be xt if t is finite, okay? And then just some whatever we want when t is infinite. Right? This is now this is a measurable. It's easy to see that this is measurable. So this is a random g valued random variable. It's a function from our omega to g, and the pullbacks of all the singletons of g are going to be events. But moreover, this thing is going to be, so then y is going to be measurable with respect to ft. It's a strict, it's being more strict because ft is a subsigma algebra. Okay? So just what you do is you can say, okay, if t was finite, I look at xt, and if t was infinite, I just do some other thing. And that is a measure, something that you can get from the information of this sigma algebra alone. These are typical examples.
Because it doesn't really care what happens at time infinity. Like, if t is infinite, it doesn't really care. Or it does care.
Well, because the sigma algebra kind of, when t is infinite, you get the whole you can observe the whole You're allowed to observe the Markov chain or the sequence up to the stopping time. So if it's infinite, you're allowed to observe the whole. Then you don't care, how this was determined.
This is just the technical of defining xt. Y is a version of xt which is finite.
Yeah,
Surely.
yeah. You have to do these things.
Yeah.
Otherwise, it just doesn't make sense. And now I can define the stored Markov property. Okay, so I want to write it in words, then make it mathematical, then prove it. Okay. So the strong Markov property following. Let P be a transition matrix. Here, yes. Of the Markov chain on G on some state space. So we have the whole thing. And then we can write of a Markov chain xt. It's our canonical process G. Okay. and let t be a stopping time. So of course, with respect to the canonical filtration, this is our assumptions. Okay, now, what does the strong Markov property say? The strong Markov property says the following. Then, conditional, writing just words, you don't have to copy this, it's just explaining what I want to do, and then I show you how to do it mathematically. Conditional on t being finite, okay? And on xt, if I know that t is finite and I know xt, okay? The process y t definition x t plus t. So if I know that t is finite and I know that that's conditioned, and I can look at a sequence which looks like this. At time 0, it's exactly xt, at time 1, it's x, next step, and so on and so forth. This has the conditional distribution has, so this is conditionally independent. This is conditionally independent. I'll write this down exactly what this means. Of the whole sigma algebra ft. So any event in the sigma algebra, okay? Conditioned on that information, it's independent of any event in that sigma algebra, and has the distribution, and I'll write and, is a Markov chain with transition matrix P. So it's just another version of the Markov chain with some starting distribution that we get from xt, and it's conditionally independent of. How do we phrase that?
Once again, if we phrase what does it mean to be canonically conditionally independent?
That's what I'm going to write down. Write it mathematically. Okay. So mathematically.
No, but the moral of it, or the no.
It means that if you ask for the probability that this process does something, and that some event that's measurable with respect to it happens, conditioned on these two things, conditional on these two things, they will factor in the conditional expectation will factor. Conditional expectation is kind of a random probability, right? So we'll factor into the product of the two things. The independent conditional on this information. What you should think about is, okay, this was again technical, so I can write this. But if I know that this happened and that I know where I am, okay, so I just start the Markov chain from that point. Random time and position. If I know where I was at that position, then I can just start the Markov chain at that point, and it's completely independent of anything, any way I got to that point. Telling me where I was at time big T, I don't need to know how I got there. So any other event that depends on the information up to that time will just not influence the future. Okay, let me write it mathematically. Mathematically, this means that for any event A in Ft, okay, now what does it mean conditionally? Conditional expectation here is something very, very simple. It's very simple. All I have to do is go over all the possibilities for this guy, right? It's a discrete, there's a discrete partition of the space. There's a countable partition of the space. So I have to go all possibilities of this guy. For every possibility, then I start from X, right? For every possibility X, is to start from X. So I can write it this way, for every A, for every X, okay? The conditional probability. And what does it mean that something has a Markov chain? All I need to tell you is that the probability that it goes to a certain point, that is the power of the matrix, right? That tells you that it's a Markov chain, right? So the probability, you can start from any new, whatever you want here, of A happening, and yt is equal to some y, okay? Conditioned on t being finite and xt equals x, the conditional information, okay? I could have also done it like this, and had everything being just a random on the other side, right? If I don't write an x here, then this is just a random variable. But I know that it's the sum of indicator xt equals x, and then for every x I get, it's this thing. Okay, so I'm just using that fact, that we have this partitioned into these countably many events. It's very simple. So this probability is equal to, what is it equal to? It's equal to the probability nu of A conditioned on times. Now, what am I timesing by? Multiplying by, start from x. My claim is that you start from x and you just look like a P Markov chain. So this means, how do I get to y in t steps? Just power of the matrix. So this is times p to the t, x goes to 1.
It's the same as just writing the probability vector nu of yt equals y, given that started from x.
Sorry, this is what? This is the probability starting from delta x, that my P Markov chain, which I can denote by x, okay, at time t is at y. Same thing. If you know where you were, then the rest looks like a new Markov chain, where deterministically start from where you were at time t.
Why is it not yt? Or this is what you were trying to
YT was a definition of something weird. I said it has the same distribution as this thing. YT is special. YT is the process. You look at the time plus t. Okay? Only conditioned on this.
So you're assuming at stopping time t you are at x and you want in
Yes,
t
yes.
little t steps to go.
Yeah.
Okay.
Those are equal as probabilities, as numbers. That doesn't mean that YT and XT are the same thing. YT and XT are different. YT looks at X. Right? What does it do? What does it do when t is infinite? I don't know, but I don't care. I don't care. The statement is only about what it does, what happens when t is finite. Okay?
I think that the other variables xt, they are like dependent on the starting point, the distribution of the starting point. Right? Like if I write nu or write delta x0, the xt is different.
Yeah, the distribution here of the XTs will be different. I'll change them.
They're not defined at one time. They're defined
so
a lot of times.
Again, when we have two pieces of data that we need when we define a Markov chain, we have the matrix and we have the starting distribution. And you have to be careful to update the starting, when you use the Markov property, you have to be careful to update the starting distribution in the correct way. Another way to write this, another way completely equivalent would be the following. Right? This was for any nu, that's why I just put it in, okay? So I start from nu, I want to look at A and YT equals Y, conditioned on this being finite and XT. So what is it? Now I'm conditioning on some sigma algebra. It's a random thing. Well, this is equal to what? This is equal to, well, first you have to do this. Okay? This is a random number. Okay? Depending on where you want to get to, okay? And then, well, you can, okay. Think about this, but then here what you do is you take t steps and you start from xt. Another random number. It's the same way as writing this.
We can write it as a sum, right?
So exactly, because this gets a countable partition of the space, then we just partition on that space, and for each one of them, we know that exactly that's what.
Then we know what is xt.
So this is a completely equivalent way of writing it, just shorthand. Instead of writing for every x, I can just write it this way. Okay, so let's prove this. I mean, it's not very difficult to prove. I think we can just basically see what we want to do. Now, I should have been careful. What I'm saying is that when this thing is this could have zero probability, right? I mean, maybe t is the stopping time when you first hit some point x prime and not x, and then you cannot write this. Okay, so what I meant by these equations was, well, the second equation is still okay. Then I could just condition. But the first equation, I have to, I cannot write this if this has a zero probability. Okay, so let me write another equivalent formulation that's what I'm actually going to prove, which makes the zeros easier. Is I can remove this line here. You see, I can do this trick. I can write a comma, and then I can write this comma here. Same thing. Because if it's zero, then I just wrote zero is equal to zero. And if it's not zero, then I just have to divide both sides by the probability, the non-zero probability of this event. That's all. Okay, so it's completely equivalent, and in fact, this is the broader statement, right? So this is the more general statement. So these two things are the same exact thing. We just have zeros sometimes, and then it's easier to write it because you don't have to worry, is it zero, is it not zero? Others I just say, okay, we take an x, if it's zero, then we're done, if it's not zero. Okay.
So that t is almost always infinite.
What?
Can it be that t is infinite everywhere?
Yeah, so then you would have, this would just say zero, you never, and then you never have, you didn't say anything in the theorem. You're talking about a zero probability event, you didn't say anything. Okay, so let's prove this. So we start, right? What do we do? We start with this assumption of, yeah. So we start with the probability. Maybe I save some. Let's start from this side. I'm erasing this. Let's start from this side and compute. Okay. So that I don't have to keep writing this again. How do we compute this? Suggestions? What should we do?
Conditional something.
Well, first of all, you have a complicated event. What do? You do the law of total probability. You partition it into smaller events that you can sum over n, 0 to infinity, right? And then you intersect the event that we have here, call this event E, intersect the event E with the event that t is equal to E. That's all. Okay, now there are no infinite ends here. Okay, there are no infinite ends. The fact that this says infinity, don't get confused. That doesn't mean n is equal to infinity, right? It never equals infinity. Okay, and this, again, if I intersect t less than infinity with t equals n, then I just get t equals n, and then I can replace all the t's with n's, right? Then I just get the sum over all the n's of probability nu of A. Let me write this way. Intersected with t equals n. Okay. Then this is intersect. This I wrote on purpose with an intersection and not with a. You'll see in a second. Then I have xn is equal to x, right? And I have yt is equal to y. But what is yt? Yt is y big T plus little t is x big T plus little t, right? But big T is n. So when I'm intersecting with this thing, it's exactly the same thing as writing x of n plus t is equal to 1.
What did you have to intersect A with t equals n?
I just wrote it this way. I mean, it's just written A intersection this, intersection this, intersection this. But I wrote, sometimes I write intersection like that, sometimes like that. Why? For my own personal reasons. Okay? So, well, I want this to be of a certain form. Okay? Now, the trick is, why did I write it this way? Okay? First of all, we have to agree that these are equal. Okay? Once they're equal, why did I write this? I wrote it this way because this guy belongs to, okay? I claim it belongs to Fn. Then I have the regular Markov property, right? Because I can pull this out, right? I mean, this conditional on this thing is independent, right? So I can condition on everything up to time n, then I just start from x, I get my thing, and I get the probability back, put the sum in. Okay? So all I need to know is that this guy actually belongs to Fn. Why does that guy belong to Fn? Okay? So So let's put a star here so that we can continue later on from this point. And I'm going to show you that is conditional, that is, so A intersect T is equal to N. Well, this is the same thing as A intersection T is less than or equal to N, but not less than or equal to N minus one. And if it's zero, then it's equality. Okay, so I can write not less than or equal to this is and not a intersection. Okay, let's intersect it with the complement of T less than or equal to N minus one. Complement. This is well defined even if N is zero, right? Just T cannot be less than or equal to minus one. Okay. So this is the same. If you're less than or equal to N, but not less than or equal to N minus one. Right? Now, this event, this is an Fn, right? This is sorry. Yeah, this is an Fn because
We took it from FT.
A is from Ft, right? That's by the definition. That's what I wanted. This guy is in
And minus
Fn
one.
minus one. The complement of an Fn minus one event. And Fn minus one is contained in Fn. Intersect the events from Fn, I get it. Same thing all the time. All these tricks, they always go. At some point, I'm going to stop writing them down for you because just get used to it. Think about it. You know, I can decide. I know that A is from F big T, right? F big T just tells me I can decide intersections of A with the stopping time. I can decide, you know, how they happen by observing everything up to this point, right? So it's very clear that's what happens. Okay, so once I have this Fn, then I can continue the computation in star very simply by just using the regular Markov property. So star is equal to what is it? I condition on this and multiply by it, right? And condition on this is the regular Markov property. This is just PT xy, right?
You are conditioning and then multiplying?
Yeah, so I can write this sum 0 to I have the sum. I have this. Okay, if it's zero, now I have to be careful. If it's zero,
It's just zero.
okay, let's give it a name. Call this whole event, we call it En. No, Enx. Enx. Okay? Enx. Okay? Depends also on X. X is fixed the way. Okay. So what do we have? We have this.
Consider the probability of A intersected with T equals N is not zero.
Just in the sum,
So we sum over all the n's such that the probability that Enx is strictly greater than zero. Okay, the new probability of Enx is strictly greater, right? Otherwise, we get zeros, right? So we sum over those. When they're greater than zero, we can condition on them. Okay.
You condition on all of.
I don't want to do it. What did the regular Markov property? Let's go back. What did the regular Markov property say? The regular Markov property says, I mean, it is that we already did this argument of conditioning, and if it's zero, then it's zero, and if it's not, then you condition. The regular Markov property says, if this is zero, the whole thing is zero. If it's not zero, right, you condition and multiply, so these separate into two products. The second one doesn't care about the past, just as T steps of the Markov chain. So the regular Markov property, so star is equal to by just the regular Markov property, not the strong one. So we're using the regular one to prove the strong one. We have this sum, okay? I don't care. I get the probability of Enx, okay? Because everything in Enx is measurable with respect to Fn. I can pull it out, take a product, and the rest, the conditional probability, or either it's zero or the conditional probability of this thing is just PT. Then here you would just get T steps of a Markov chain started at X.
This is the base form.
It's not even base formula, it's just the fact that, the Markov property says if you give me information up to time n and where I was at time n, then they just factor into product of two, where the continuation is just the same as the original Markov chain. Started at X. Okay,
In the Markov property, I only have to condition on xn equals to x, right? But Fn does not add any information.
the Markov property says something like this. You have probability nu of some A in Fn, any event in Fn, and xn equals to x, and xn plus t equals to y, then this is equal to just probability of this thing times pt xy. That's what the Markov property says. It's basically what I wrote, okay? And how do you prove it? Well, you say either I condition on this whole thing, either this thing has probability 0 and then it's equal because it'll be 0 on the other side, or this doesn't have probability, so when I condition on it, then I know that this becomes pt xy, and I have to multiply because I conditioned. Okay, so that's just, so what I wrote here is just the regular Markov property. It's exactly the Markov property. But then when I pull it back, what is this sum? There's no n here anymore. What is this sum? If I look at the event, which I just wrote down, right? I'm summing over all the possibilities, t equals n, right? The others, well, this is xn, so I can put it back to x big T, right? So the others don't look at n, and the only thing is I need a disjoint union of t equals n over all n's. That's t finite. Don't, right? So you have to be careful that so this is equal because the disjoint union, n goes from 0 to infinity of t equals n. This is not everything, like we were used to maybe in because we could also get infinite values. So this is exactly the event t is less than infinity. Okay, and then I'm just using law of total probability. So this becomes a probability nu of, when I sum these, I get a, I get t less than infinity, I get xt equals x times pt xy, which is exactly what I wanted to prove, right? Okay, so I was being very meticulous with the details, but you should. It's simple. It's not like the idea is very easy. It's just maybe technical to be careful with the details. Okay, so this was the Markov property, the strong Markov property, and do some maybe sample in a minute, in 10 minutes. Okay. Now, what I want to do is I want to talk about green functions. So, do you remember? Well, okay. So, if you've done like I don't know, you learned Green's identity, calculus 3, 4.
I didn't do with the integral.
Yeah, just integrals in Rn or whatever. Okay, so we'll see that today, tomorrow, maybe. We'll see Green's identity, what it means. Actually, much easier than in calculus. But I think this gives the proper intuition behind what's going on.
I think a few things that are called Green's identity.
Yeah, there are 3, but there's the basic one. Okay, I'll you don't need to know it. So here's the what?
Green's theorem.
It's basically integration by parts. Integration by parts is like the one-dimensional version of it. So, but I'll say what it is. Let's see. So here's before we get to Green's identity, I want to Green's function. So Green's function in classical analysis is the following function. You take the Laplacian. What is the Laplacian? Laplacian is the sum of the second derivatives. So you have vector functions on vector spaces, functions on Rn. Okay, take the sum of the second derivatives, and then
By every variable.
and then you can find a function that you when you apply this sum of second derivatives, right? All partial second derivatives, then you get delta 0 or something like that of your space. You get the delta function. You can solve this equation. Okay, so in one dimension, I'll just say you can solve the equation second derivative of g is equal to delta 0. Now you cannot solve that equation, right? But
What is delta 0?
Dirac delta at 0. Function which is infinite at 0 and 0 everywhere else.
It's 0 everywhere else, and it has the integral 1.
Okay. So
0 almost
so you see, everything doesn't make sense, but here in our world, it's going to make sense very easy, very easy. Really, you don't need to do distributions. You don't need to do anything sophisticated. You'll see it in a minute, but it's basically that. Going to be the exact counterpart of all the things you see in classical analysis. We're going to do them here. Sometimes it's harder, sometimes it's easier. Okay, so I want to say what Green's function is, and you're going to see it. I'm going to define it, and you're not going to see why that is. Maybe tomorrow I think I'll show why it is the counterpart of what I just wrote. At least partially show, maybe not fully.
Is
So-
it more to do with the harmonic function?
Yes, very much to do with harmonic.
The
Yeah. Also, Green's function is used to give solutions of harmonic functions in Rn. Define what harmonicity is in Rn, and I'm going to talk about that. I'm going to talk. Green's function is very important for harmonic functions in Rn, and it's very important for harmonic functions on networks, which is the maybe broad generality that we'll talk about. So, but before we go into networks, let's just look at general Markov chains. I didn't even, but irreducible. Remember, what is an irreducible Markov chain? It's a connected Markov chain. It's a Markov chain where every state can reach every other state. Right? So when I write irreducible, it means that for any two states, there is some P such that P, T, X, Y is positive. You can go in a positive, maybe tiny probability, but there is some way to get from X to Y. They're not in different universes. They're in the same universe. Okay, so it's a connected object in a certain sense. Okay, so so we're doing an example. Okay, we're doing an example, and you can think of this is called excursion, sometimes decomposition. Method that you use in Markov chains. I'm going to show something about strong Markov problem. Excursion decomposition. So we have xt is going to be a Markov chain with transition matrix P. Let's just start writing Markov P instead of all of these words. Okay, has transition matrix P, and it's irreducible. So the matrix is irreducible, or the Markov chain is irreducible, same thing, meaning for every x, y, I'm writing it, there exists a T, such as P, T, X, Y, is strictly positive. And get from X to Y. Doesn't mean that the same T works to go back from Y to X. Maybe you can get from X to Y in one step, and from Y to X, you need 1 million steps. Could be. And it doesn't mean that every T works, right? If you take the transition matrix of the random walk on the tiles here, when I go left, right, up and down, right? At even times, I can only be at even tiles, and at odd times, I can only be at odd tiles, right? So bipartite.
It's also non-periodic, then you have such.
Yeah. So I didn't say what non-periodic.
Yeah.
You said a word that's we don't know.
Yeah.
Know. You said a word in a different language, so it doesn't help us. So we didn't say anything about periodicity, and I probably won't go into it unless I start talking about finite state convergence. Okay. So what do I want to do? I want to define excursions. What are excursions? Excursions are basically you have a point X. Okay. You start from that X. You walk around on your space. This is this random motion. It's not really a line, right? It's jumping around space, and at some point you come back to X. That's an excursion from X. Excursion means you go out, you come back, right? Okay. That's what I'm thinking of. So how can I define that? Well, let's define inductively. We're going to define some times, random times. Okay. First time is first of all 0. T0 is 0. Okay. Then, or we should write it. Well, everything. Okay. Everything depends on X. So we have X. We fix some X inside. We'll write G. G is our state space. Okay.
So you begin with X.
Yeah. So Tx 0 here, not a power, but just an index, is going to be 0. So just random time depends on X. I have to remember my X. Okay. Then maybe it's better to write the X on top. Okay. Write X here. Okay. Let's put the X on top and the 0 on the bottom. So remember, it depends on X. Then we define Tx of k plus 1. Okay. Or any. So I already defined 0. So for any k in the natural numbers, I can define tk plus 1. This is going to be defined by the infimum over all possible t, okay, which are strictly greater than tk x, okay? than the previous one, such that xt is equal to x. So what is tkx? It's the kth arrival to x, where 0 is weird. Okay, 0 is weird. 0 is always 0. But then if you started at x, then t1 would be the second time you're at x, or the first time after 0 that you were at x. Okay? So tk would be the kth time after 0 that you were at x. If you don't start from x, it's the same as just the kth time you're at x. And if you start from x, then it's the k plus 1 time that you're at x. But just have to be careful about that. Okay? Now, I didn't say you have to check that these are stopping times, and they are stopping times. Basically, it's always true. Well, I told you the first hitting time of a guy is a stopping time. And whenever you have a stopping time and you take the infimum over all t after that stopping time, that you hit something, could be a different thing, that would also be a stopping time. So exercise pkx is a stopping time for every k. Always a stopping time. Could be infinite. When is it infinite? Convention, I should have written this here. Convention infimum of empty set is infinite. Okay? Could be no t's. You never hit x. So you kind of didn't have anything to do the infimum, so you're stuck at infinity.
What if you're irreducible? Does not mean that you eat x?
No.
Right?
No.
You can go with a.
You can go on forever. It's a random thing. You can go on forever. There are sequences. There
Do you have a positive probability?
There are many. In fact, it's very rare to have, definitely for random walks on groups, there are basically only 2 groups for which you're guaranteed to hit a certain cycle.
That is it too.
We will see that in the future. And okay, so it's a rare. Big things, you run away to infinity. You're not guaranteed to hit x at all. Of course, you can construct general Markov chains for which you can make x's, guaranteed to hit, even though you do many. General Markov chains are too wild to classify. So exercise, you check that there's a stopping time, and then we can look at an excursion. So what is now, I want to write down mathematically, what is the kth excursion? Okay, so I can write maybe EK, which is going to be the kth excursion, right? So EK, the kth excursion, is going to be
Excursion that you.
What do they?
excursion is a gicha. Okay. So excursion, the kth excursion, I'm just going to define it. There's going to be a finite sequence, or maybe sequence of vertices. Okay, so it's going to be the sequence. Well, you start at. Okay, so it's not going to be okay. So we can define it if the kth time is finite. Then we can define EK, which is going to be XT.
Finite in any sense.
So let's start from K and go to K plus 1, okay? And then we go to K plus 1. And this is, let's define it if K plus 1 is 5, okay? It was infinite anyway.
Like almost surely, or
No, I mean, this is just notation. I can define this to be that when it's finite, and if it's not finite, then I don't know what I defined. I don't care because it will never come up. Arbitrary sum, arbitrary value. It is just notation. It's not really.
this is a sequence, isn't it? Is a sequence of x.
It's a sequence of states.
It's the same, isn't it the same state?
This one and this one, but there are lots of guys. Okay.
This is the path you take.
Path.
The case excursion.
Okay.
Then I do
Plus,
K
Yeah.
x plus 1, plus 1 not on the K, on the thing,
Yeah.
on the time. And then I go all the way up to xt K plus 1 x.
Yeah, okay, sorry.
Right? So it's just x. Okay. It could be infinite. could be infinite. If this was infinite, then it would be infinite, but so that's why I wrote it down. It's just shorthand so that I can write things, right? Now, another thing we should notice is that these guys are increasing, right? I mean, it's obvious that they're increasing, right? So in fact, strictly increasing. Because every time you define it with the first t, strictly bigger than. Well, okay, if they're equal, it means they're infinite. They're both infinite. So pkx finite implies that this is the case. Okay, and in general, just have inequality, which means if you have equality, then they're both infinite.
You can also have like a sort of lazy Markov chain where you can stay at the point, or
But the type of go one by.
you wouldn't call it an excursion if it's.
No, it will just have two guys here. Yeah, I never said in my transition matrix that pxx is 0. Maybe pxx is 1/2, right? Or something like that. Maybe it's positive, right? And this would mean that there's a half probability that, when you're at x, that you just come back to x. It's just a schematic line. It's not a real, right? It's an abstract space. It could be the next step at x, and then this would equal to, if tk, it could be that tk is 5 and tk plus 1 is 6. And just here you write x. That's what's written here. But it could be x, y, z, something, and then x. What you know is that in between the two things, if there is something in between, there's no x's. That's what you know. Okay. Good. So now, if you think about it, the walk, what is it? The walk, I call it the walk. The Markov chain, what does it look like? It starts from somewhere. I don't know where it starts from, maybe even a distribution, right? And then it goes and it hits x for the first time at some point, maybe never, but if it does, right? So this is a special part. But then we're just decomposing according to the number of excursions, and at some point it goes to infinity. Now, intuitively, what happens? How many times do you visit x? Well, you have to hit x in order to visit x. Okay, suppose you hit x, right? Let's suppose we start from x. Okay, suppose we start from special, right? So how many times are you at x? Well, you're one time at x for sure, because you start at x. Then what is it? Then maybe you come back to x, maybe you don't, right? But if you do, these are stopping times. Condition on that. What's your distribution? Your distribution is just the distribution of what you were at the stopping time, which is delta x, right? Deterministic at x, then continue. So you get an equation for, visiting x k times, or for the distribution of how many times. This is just a geometric distribution. Just a geometric distribution. Okay? So I claim, okay, so let's define the number of visits to x. In fact, I'm going to write this guy down. Let me already introduce you to my green function. Okay? I'm going to write this one down. It's going to be a 2-point function. States. I'm going just to define, it's just definition. I'm going to write this sum, where t goes from 0 to infinity. Okay? The probability that I start at x and go to 1. My x is fixed, so let's reverse these guys, okay? Well, general definition. We're going to use this definition throughout the course. Okay? Now, first of all, you can ask me, does this sum converge? Maybe it doesn't, but that does make sense because it's a sum of non-negative numbers. It was either plus infinity or some finite sum. Okay, I'm allowed to write this. I don't have any contradictions here. Be careful if I want to take differences of things like this here. Okay? I can write this. Second, what does this say? This says, just developing this thing, it says the sum for all t goes from 0 to infinity of the expectation, right? Starting from A. So when I write PA or EA, I mean delta A, right? That's what I mean. Right? Of the indicator that at time t, I was at B. I didn't do anything. I just rewrote what's written there. But now these are non-negative random variables. I'm summing an countable infinite sum, right? So I can pull the sum inside. Why? Because,
Sort of monotone conversion.
well, it is exactly monotone convergence. Exactly monotone. Partial sums monotonely converge, and you can get from monotone sum, you can also get infinite. Monotone convergence works also for infinite. So monotone convergence, this is equal to pull the expectation outside, sum from 0 to infinity of 1 xt equals b. What does this say?
The expected number of visits.
This is not the expected. This is the expected.
Yeah.
This is exactly just the number of times you visit B, the random number of times you visit B, which can be infinite. This is not a random variable in the strict sense, in the intro to probability sense that it takes values in R. It takes values in n union infinity. Right? It counts, so it takes union natural numbers, but it could be infinite. Just counts how many times I visit B.
Starting from A.
Starting from A. So the green function, definition of the green function, GAB for two states is you start from A. I didn't say it's symmetric. I didn't say it's symmetric. There's no reason to think it's symmetric. In fact, it's not in the most general case. We will see what symmetries it does have, okay? But A and B are playing a completely different role. So, you know, I should have introduced a line here or something like that to tell you it's not symmetric in A and B. A is where you start from, B is who you want to visit. And you just count how many times you visit. Well, this is accepted notation, and you'll see it does have symmetry. It does have symmetry. We'll see what symmetries it has, at least in the reversible case. So you count how many times you visit B, the expected number of times you visit B, starting at A. Okay, let's call this guy. For our process, let's just call that B. And in fact, all I want to do is I want to okay, I'll just keep sums. I'll just write sums. But you remember, when I'm summing these indicators, I'm getting, maybe I'll get tired, I'll put the V's in, but V's for visits, right? So how many times do you visit B? Maybe I want to do it up to a certain number of times or something like that. So, okay, you know what, so I'm gonna write this. V T of X, this is going to be the sum, okay, from J equals 0 to T, indicator xt equals X. Okay, number of times you visit X, random number of times you visit X. This is good for T, and it's even good for T, which is infinite. With finite T, this is always finite, it's at most T plus 1. It includes time 0, and that really depends on your starting distribution. So that's the notation I want. Now I want you to notice that if I start from X, I don't have this problem of the first path, right? And I get an equality of events. Remember my stopping times. I'm really having this discussion with you to teach you a method. It's not like there's not going to be an important theorem, just teaching you a method. Well, there's going to be a nice theorem at the end, but just teaching you a method of how to look at these random processes, right? So, if I want to work under the measure where I start from X, the delta X starting distribution, right? And my claim is that I look at V infinity of X greater or equal than K. Okay, this thing. Intersected with x0 equals x. Okay, if I know that I'm x0 equals x, I mean, I could have also written that these are equal under the measure, up to measure 0, under they're almost surely equal under the measure px. Okay, what is this event? This event is just that I visit at least k times x, right? And the first time also was included, right? What does this mean? This is the same exact thing. I visit X, I have the first time, and I have to come back to X at least k minus 1 times, right? So, so this means that T, K, X is finite. TKX is finite. It means that I saw myself at xk times, including x0.
Finite time.
Yeah, I mean, saying that this thing is at least k means that I know that I came back to, maybe I did more come back, maybe not, maybe tk plus 1 is already infinite, I don't know. It is exactly the same event. Sequences go in here, go in here. So we can actually compute this probability using a strong Markov problem. Okay, let's see how we do it. We fix some k. Okay, so fix some k. Probability starting at x that v infinite x is greater or equal than k. I want to fix some k which is greater than 1. Strictly greater than 1. Natural number strictly greater than 1. What is the probability that I visit x at least k greater than 1 times? If I start from x, k, putting a k equals 1 there gives me probability 1. Start from x, you have 1 visit. Okay, greater than 1, you already get a non-trivial statement. Okay, well, let's compute. This is equal to the same thing, probability starting from x, the same event that dkx is finite. Same event, same under this probability measure. These differ by measure 0.
The notation of p of x is just conditioning on x0 equals to x, it's the same thing.
Yeah, px
The conditional.
Yeah, just conditioning on the starting at the starting distribution is a delta mass at x. Okay. Okay. So this is dk is finite. Now remember, these are non-decreasing. It means that all the previous ones are finite as well. Right? So I can write this. I don't lose anything by writing this. Right? Didn't get any new information. I mean, the intersection of this event is just this event. Okay? But then I can. By the way, why am I allowed to do this? Why does this always have positive? I didn't say. Why does this event always have a positive probability?
Because k is greater than 1 and started at x.
No. Why does the probability that I hit x always have a positive probability? Maybe I never hit x. It happens with probability 0. Why can I condition it? Because it's irreducible. That's why I assumed it was written here that I assume that it's irreducible. Right? Every x and y, there is some positive probability to go from x and y in a certain number of steps. Right? So you take an x, as long as your point has one, well, if your Markov chain has 1 point, then we're not doing anything, we're just staying at x, right? Markov chain takes some other y, right? In fact, we're only really interested in, well, if it's finite also, finite and irreducible then. But you take some other y, you can go to that y in some t steps, then you can go from y to x in some t prime steps. So in t plus t prime steps, there is a positive probability to go from x back to x. So there's always a positive probability to come back to x. You want to do it k minus 1 or k times, then it still has positive probability. So I'm allowed to condition on this event.
Now it just be a multiplication of the same probability.
And now this, we have a k minus 1 here, okay? And what is this? I conditioned on a finite stopping time. And, you know, I could have added, maybe I should have done that.
This is just T2.
What if let me write it this way. Tk minus 1x finite, or tk x finite. I claim that this is equal to tkx finite and xtk x equals x. Is this correct? It's because the way this is defined is that if it happens, you have to be at x. Okay? There's no other way to do it. So this is the same exact event. This is really the same exact event as this, which is when I condition here, just so that you formally remember, because if you remember, formally we had conditional on we know where right? We have to understand what is the distribution where we're at this time. So the distribution here is delta at x. I mean, that's why we use this kind
Do you
of.
want to write tk minus one there or tk?
Well, it's true for every k. True for every k. This is a general statement, just that these stopping times are defined in a way that at those stopping times, they can either be infinite, but if they're finite, you have to be at x. There's no other way. This is by definition. Any omega that comes in here has to satisfy the x, t, k, x of omega is x. Okay? So I use it with k minus one here, just to put this, formally to put this. But if you want to think of it, I'm just conditioning what happens up to time t, the stopping time tk minus one. How does it look? Well, I know where I am. I'm at x by definition. And the rest continues like a Markov chain started at x. So now what is this? This whole number is you start at x with a Markov chain, right? And you're looking at what is the probability that the next time you're at x, what is the probability that happens at a finite time? So if I want to write this as a number, this is the probability that starting the Markov chain at x, the next time I'm at x, that's t1, is fine. You see how this transforms into this? It's completely different. This is a different stopping time, but these two probabilities are the same. And this is the strong Markov property.
Going from
This probability to this probability.
as long as you are in x, you have the same probability going again to
The
x.
rest, the new Markov chain started at this random time, looks like a Markov, just looks like a regular Markov chain started at x. So this event for that new Markov chain is the event that that Markov chain hits, but that Markov chain has the same distribution as the original Markov chain. Okay? So in probabilities, these are not the same events, but they're the same. This conditional probability, the number that's written here is the same as the number that's written here.
For example, if you wrote tk minus 2, then this would be equal to t2.
Right? Yeah. Because they're the same, and it's very important that I have starting from x here. If I wasn't starting from x, it wouldn't be true. Because this one starts from x. Okay, so here I could put a general probabilities distribution if k is not 0 here, okay? But once I know that I was at x, coming back to x, this would turn into an x anyway. So from a general probability distribution, I would turn this into an x.
So you don't really need the x.
What?
You don't really need the x over there.
I don't need it for this transformation, but soon we'll see some connections here, and we would have to take separate care of the first arrival to x.
But we just like we want to write t like 2, right? Because or
No, t1. t0 is 0. In this case, t1 is already the second time you're at x, but it's the first time after 0 that you're at x. That's how we defined it. You have to be very careful. You define it properly. Okay? And this is times this probability. But what is this probability? This probability is a probability that this is greater than k minus 1. Right? Let me write it. Now, we know the initial condition of v, right? The probability that when you start from x, probability that you have at least one visit is 1, because you're always starting at x, so you always get one visit. V counts times 0 as well. Okay, so if we would have here a 1, we would be done. Okay, so but we can continue. So we start with a k bigger than 1, and we keep going down. Oh, I want to go down again. I get hit with this. Does that depend on k? How many times do I do this? Right? You want this is a proof by induction, but it's kind of a recursive equation, so you can also. Okay. How many times do I do this? I do this, right? Every time I do it, once I get a -1 here, and I want to end with 1, so I do it k minus 1 times. Okay. And so what do I get at the end after I do it k minus 1 times? I get. Let me erase this. I get that this is equal to, I have that number, this number, right? It's the probability of completing a first excursion, like start at x, come back to x. Doesn't have to be one, this probability. It could be that you run away from X. Okay? This thing to the power K, whole thing to the power K. Take a number, multiply it by itself. If it's one, then you just get one. Okay?
K minus one.
K minus one. Thank you. K minus one. Very good. Okay? And that was important actually. You do K minus one times, and then what do you get here? You get probability starting at X that V infinity X visit X, including time 0, at least one time. Well, this is 1. Okay? So we just get that equation. See the equation? Right? Very cool. We can get it. We did some real computation here. Okay, but then this begs, what does this beg me to do? I have a number to the power of K. Right? Take a sum. Come on, you have to. Geometric thing. First of all, I want you to notice, what does this mean? This already gives me the complete distribution of this random variable. This random variable takes values, okay, in the natural numbers, maybe infinity, the V infinity, X, right? If you check, so we have two cases, maybe pass to a different color. So we have two cases. One case is if the probability starting at X that T1X is, the probability of coming back to X is 1. This is a possibility. This is a possibility. For example, maybe you have finitely many states, or maybe, I don't know.
Random walk.
We're doing it on Z.
Well, yeah, on Z we already proved it. Yes, okay. So if it was a simple random walk on Z, right? We already showed that this is the case. Okay, so you have 1 here, right? And so you get that you visit at least K times with probability 1. So it just tells you that if you come back once with probability 1, you come back infinitely many times with probability. So if this, then let me write it in a very weird way. Okay, let me write it in a very weird way. Then the G. Okay, so then V infinity X, not right, is equal to infinite. Starting from X, the probability that Vx is equal to infinity is 1 as well. Right? Okay? And specifically, if it's equal to 1, if it's equal to infinity with probability 1, then it also has infinite expectation. Okay? This is a weaker statement. It's a much weaker statement, right? You can have infinite expectation even if you're finite, almost surely, right? Okay? That's one case. Case 2 is if this probability was finite. Finite meaning less than 1. Okay? If the probability, it's always finite. Right? So like 0, talking like a physicist. If it's less than 1, it's always greater than 0, I explained, because we assume that it's irreducible, right? Irreducible tells you, yeah, you're right, it could be 0. Then this whole thing would not have worked because I couldn't condition. This is greater than 0 because of irreducibility. Okay? So if it's less than 1, what did I write here? I just wrote, you say, okay, I have the K minus 1, you have to be a bit careful, but I just proved that under Px, so in the space where I already put the probability measure, so in this probability space, random variable, if you change the probability space, it changes its distribution. Distribution on the same space depends on the probability measure you put there, right? But under now, when I have the triple, when I have my omega, my g to the n, my f, my px, under this measure, I can tell you what the distribution of that guy is. The distribution in the sense of introduction to probability, right? It has values in the natural numbers. And I know that something that looks like this, I know what it is. It's exactly geometric. And V infinity X has geometric distribution. Okay? What is the parameter? The parameter is, right? We know what the parameter for geometric is. The probability that you're bigger, strictly bigger than 1, right? I mean, that's the parameter for, right? So, I mean, this is 1 minus, right? So the parameter is 1 minus this guy. What is 1 minus that guy? It's the probability of the complement of the event. So it's a probability starting from X that you escape. This is sometimes called the escape probability. It equals infinity. Which, in this case, this is a positive. Well, I could write geometric here where this is 1. where this is zero, right? Geometric zero is something which is, if you toss infinitely many coins that come up heads with probability zero and wait for the first heads, you're going to wait infinitely many coin tosses, probability one, right? So actually these two cases are the same.
Just make sure, because I don't fully remember what's the geometric
Geometric random variable is tossing a coin. It lands heads with probability P and counting how many times did I toss the coin
first.
until I saw the first heads. Okay, so if P is zero, you wait infinitely long with probability one. That's the first one. If P is strictly bigger than zero, this is the P, which is one minus that, which is this case, right? Then, well, we know lots of things about this, but the first thing is that it's always finite almost surely. Okay, it won't be infinite with probability one. Okay, and second of all, I mean, this exactly characterizes that distribution. Any random variable that satisfies this equation will have to be such a geometric.
When calculating the distribution, you have to look at less than, right? Less.
Yeah, so the distribution function will be some other thing, but because this only gets values in the natural numbers and well, you can compute this. It's enough to say this to know that this has a geometric distribution. So that's an exercise.
You said something to do with no memory or something like that.
Yes, it has no memory. So if you know that you waited,
Markov chain?
if you know that you did, look, that's exactly a strong Markov property. If you know that you visited 8 times already, okay? Then what is the probability that you have n more visits? It's just restart the Markov chain and do n more visits. That's memoryless. So you should have already, I actually proved this in most years I prove it, that the only random variable, the values in the natural numbers or values in the integers even that has the memoryless property is the geometric distribution. So this is another way to say strong Markov property is telling you that this thing has memoryless. Okay? What it's telling you, right? Because you know how many that you visited more than a certain amount. What is the probability that you just restart the Markov chain given the information that you have? Yes.
The same works if I replace point X with
No.
general subset.
No, because when a general subset, I come back to different points, I don't know where I start from. And it could be that starting here, I get a different return distribution, and starting here, I have to have some way of saying that when I restart, I start with the same distribution. See, the thing is, when we did this transformation here, we got the next. We always got the same distribution. Okay? And if it was a set, then I don't know, with some probability I would have an X, some probability I have Y, and then I get a mixture of things, and it's not clear that every time I get the same one. So it's not going to be a geometric. You can still do excursion decompositions in the sense that you will have products of things, but each one will depend on the previous ones, and it will be very complicated.
Like
Could be.
a group or something like that.
What?
It was like a subgroup or something that's.
Yeah, so
more
subgroup is, we'll see what we do with subgroups. We'll do something with subgroups. Well, yeah. Subgroups is different because you have more structure. More structure. There is some symmetry. You have a subgroup. Okay? Cosets looks the same, in a sense. Okay? But in general Markov chains, if you have a set, maybe if you come into a set, you walk around the set, then you leave at some point. So if you leave here, maybe you think of this. I have one edge, and this is connected to some graph, and this is connected to a completely different graph. And I'm counting the number of visits to the two of them as a pair. But it depends when you exit, right? I go out here, I'm doing something, I get a certain distribution to come back to this one. But maybe I do one step here, so I count another visit, and then I go out here and I get a completely different distribution. Right. So it becomes much more complicated. And this is even a simple case where you can analyze it by doing some kind of analysis. But the more points you put in the set, and the more wild.
Generally, if you take your space and partition it to disjoint subsets, and you have a Markov chain on this partition.
That's not Markov anymore. I tell you that you're in a certain subset. You don't know how you're distributed in the subset. This is what's called a hidden Markov chain. Completely, it's a difficult thing to analyze. And in fact, you could basically do whatever you want. Okay. So this excursion decomposition is very nice because we got, get the exact distribution of just using strong Markov property, we get exact distribution of the number of visits. You see, it just depends on when returning to X, right? It just depends on the probability of returning to X. Is it 1 or is it less than 1, right? And we know the exact distribution. One more formula that we should have is we get the expectation of V infinity X, right? Expectation under X, okay? What is this expectation? We know it's 1 over this, right? Okay, 1 over that.
So that also makes sense if it's 0, right?
Yes, makes sense if it's 0. But that's a weaker statement. Okay, so you know how in expectation how many times you come back to X? If you count the first step as 1, you don't want to count the first step as 1, then you just write this as 1 plus something, so you need to move the 1 to the other side, right? Okay. But what does this tell us about the green function? What is this? This is gxx. Okay. So I want you to notice something you asked me before. Can it be that you have to come back to X or you don't have to come, right? So already we see something. If you start at X, we'll see that it doesn't matter that you start at X for this qualitative statement. But for the moment, what we see is that to determine this guy, right? To determine whether I escape X or not. Just to determine whether I escape X or not, right? So this thing will be positive. This thing will be positive if and only if, what? If and only if the expected number of returns to X is finite. The expected number of visits to X, this is what I call gxx. So this was an infinite sum which converged. So convergence of this sum is equivalent to the positivity of this number.
This is the definition of recurrence.
This is the definition of transience. This means that escape with positive probability.
Recurrence means
And if and only if.
Yeah.
Recurrence would mean that this would be 0.
Yeah.
And that would be equivalent to the green function divergent. This green function is very important. In fact, if you can think about it, what I did when I did GAB was I summed these things. Last remark for today, and this we will forget and come back to it maybe in the future. Okay? So I summed this. And I said, okay, convergence or not, this always makes sense, but I can talk about convergent or not, right? And it converges exactly when I can escape. Okay? At least for B equals A, at least for diagonal. We'll see that it's, once you have it for any pair, you get it for all the others, but at least for irreducible trees. Okay? But I could have also, you see, I have this, I fixed some A and B, maybe A equals A, maybe A equals B. And I look at the sequence of numbers and I want to understand something about them, right? And so one way to understand something about sequences of numbers is to write like a little generating function here. I'm gonna do this, right? So I take some number, maybe this is a complex number or something, right? Maybe it has modulus less than 1. Okay? Right, so one way to understand things about sequences, some people like to look at, you take the generating function for that sequence, right? This is a discrete math kind of method, right? It's an analysis, certain types of analysis kind of method. Okay? And you see, what I did here was I just took this function. So first of all, it converges for all these guys, for psi less than 1, right? And as soon as you get bigger than 1, then this is going to explode. Because these are non-negative numbers, and you take, well, okay, not for all time. Oh, okay, not in all cases, but take psi too big, then this is going to explode. So you have to be careful. That was a deep statement. The fact that these things can decrease, have to decrease at most, the fastest they can decrease is exponential. You have to be careful. Why it's true. But anyway, but at psi, if you take psi equals 1 or absolute value 1 or something like that, then you can ask, do I have convergence, right? Even if the radius of convergence is exactly 1. Okay. So this question is, you know, this is a deep thing when you look at, when you put in this variable. We're only looking at like one instance of this function, right? So it does help. And there are ways to analyze random walks by looking at this, you know, green function as a generating function and not as a, but we're going to look at the green function just as a function of the guys here and not as putting psi equals 1. Always just expect the number of visits when you start from A, how many times you visit B in expectation. Okay? And we saw that this is related to the escape probability. Makes sense. I mean, it makes sense. If you can escape, then you should visit only finitely many times, because every time you visit, strong Markov property tells you that you try to escape, don't succeed, try to escape again, don't succeed, try to escape again. What does it mean don't succeed? It means you come back to X. That's exactly what we wrote. I mean, what I said in the last sentence is exactly this whole last hour. Okay?
Strong Markov properties